0 seconds. The engine stops, not gradually, not with a warning. One moment the engine room is producing 80 megawatts of power, running at a continuous deep roar that you feel in your feet, your chest, your teeth. The next moment, there is nothing. The sound does not fade, it stops. In the sudden silence, you can hear the cooling fans spinning down, the hum of electrical systems dying, the creak of the hull in the water, and then, almost nothing. This is what a ship blackout actually sounds like. Not alarms, not explosions, silence. And in that silence, the clock starts. Because a ship without power is not a ship. It is a very large object at the mercy of wind, current, and whatever happens to be nearby. What happens in the next 60 seconds determines everything. Most people who have watched coverage of the MV Dali, the container ship that struck the Francis Scott Key Bridge in Baltimore in March 2024, remember the images. The bridge collapsing, the ship with its lights flickering. But fewer people understand what was happening inside that ship in the seconds before impact. The crew lost power. They attempted a black start, the emergency procedure to restart a dead ship from zero. They did not have enough time. 60 seconds is not a long time, but it is exactly long enough to understand why some ships survive a blackout and some do not. Let me take you through every second. 0 to 5 seconds. The main engine stops. The propeller, which was turning at 80 to 100 revolutions per minute, begins to slow. It will not stop immediately. A propeller that large has enormous rotational inertia, but it is no longer producing thrust. On the bridge, the steering wheel goes slack. The hydraulic steering gear, which requires electrical power to operate its pumps, has lost pressure. The rudder stays at whatever angle it was at when power died. It will not move again until hydraulic power is restored. The radar screens go dark. The GPS display goes dark. The electronic chart system goes dark. The bridge, which seconds ago was a room full of glowing displays and instrument lights, is now lit only by the faint emergency strip lighting running on battery backup. The officer on watch reaches for the radio. The radio is also on battery backup, but the main communication systems are down. In the engine room, 7 decks below, the fuel pumps stop. The lubricating oil pumps stop. The cooling water pumps stop. The chief engineer, if he is there, already knows what has happened. Every gauge on every panel has dropped to 0 simultaneously. 5 to 15 seconds. This is the dead ship phase. The vessel is now coasting on whatever speed it had when power died. It has no propulsion, no steering, and almost no instrumentation. It is subject entirely to external forces: wind, current, wave action. If the ship was an open ocean when this happened, those external forces will slowly push it beam on to the sea. In heavy weather, this can become dangerous within minutes. The ship will begin to roll more severely as it loses the stabilizing effect of forward motion through the water. If the ship was in a channel, approaching a port, or near any fixed structure, a bridge, a reef, a coastline, the situation is immediately critical. The ship is still moving at whatever speed it had. It has no way to stop and no way to steer. The Dali was in the shipping channel approaching the Francis Scott Key Bridge when power was lost. The ship was moving. The bridge was ahead, and the clock was running. 15 to 30 seconds. If the ship's emergency systems are functioning correctly, something happens at around the 15-second mark that changes everything. The emergency generator starts. The emergency generator is a completely separate power source from the main system. It is located in a dedicated compartment, physically isolated from the main engine room, typically higher in the ship, away from the flooding risk of lower decks. It has its own fuel supply, its own cooling system, and its own automatic starting mechanism. International maritime regulations require the emergency generator to reach full operating speed and take electrical load within 45 seconds of a main power failure. On most modern vessels, this happens in 15 to 30 seconds. The emergency generator does not restore full ship power. It cannot. Its output is typically between 500 and 1,500 kilowatts, compared to the 60 to 120 megawatts that the main system was producing. It is enough to run the critical safety systems, nothing more. 30 to 45 seconds. The emergency switchboard comes alive. Power flows to the systems that the naval architects and regulators determined, long before this ship was built, must have power before anything else. Emergency lighting activates throughout the ship. Not full lighting, the battery-backed strip lights that mark escape routes and critical equipment. Enough to see. Navigation lights come back on. A ship without navigation lights in a shipping channel is an invisible hazard to every other vessel in the area. The regulations are absolute on this point. Navigation lights must be restored within 45 seconds. Internal communications are restored. The bridge can now talk to the engine room. The engine room can report status. For the first time since the blackout, the crew has a shared picture of what is happening. The fire detection system reboots. This matters enormously. A blackout can cause electrical faults that start fires, and detecting them in the first minutes is critical. One steering gear motor, one of typically 2 or 4, receives power from the emergency switchboard. The rudder can move again, but slowly and with reduced force. The radio comes fully online. If the ship is in imminent danger, this is the moment when the bridge can transmit a mayday. On the Dali, the crew transmitted a warning to the bridge authority in time for police to stop traffic on the Francis Scott Key Bridge before the collision. That warning, made possible by restored communications, saved an unknown number of lives. The bridge itself could not be saved. 45 to 60 seconds. The engineers are already in motion. A black start, the procedure to restart a completely dead ship from zero electrical power, requires a specific sequence of actions, each one dependent on the one before it. There is no shortcut. There is no faster way. The physics of the machinery determine the order. Step 1. Compressed air. Large marine diesel engines do not start with a battery like a car engine. They start with high-pressure compressed air, typically at 25 to 30 bar, blasted into the cylinders to force the pistons through their first revolutions until the engine can sustain itself on fuel combustion. The compressed air is stored in large air receivers, pressure vessels located in the engine room. If those receivers are charged, the air is available immediately. If they were depleted before the blackout, which can happen if the ship had been maneuvering heavily, they must be recharged using an emergency air compressor running on power from the emergency generator. This is the critical choke point of the black start. If the air receivers are empty and the emergency compressor is slow, the restart is delayed by minutes. Minutes that may not be available. Step 2. Fuel and lubrication. Before the main engine can be started, the fuel system must be pressurized and the lubrication oil system must be running. Starting a large marine diesel engine without pre-lubrication risks immediate and catastrophic bearing damage. The bearings that support the crankshaft require a continuous oil film before the engine rotates. The engineers manually start the auxiliary fuel pumps and lube oil pumps using power from the emergency generator. They check pressures. They verify temperatures. They confirm that the fuel heating system, which keeps heavy fuel oil at the 120 to 150 degrees Celsius required for combustion, is maintaining temperature. If the fuel has cooled significantly during the blackout, it may have thickened to the point where it cannot flow through the system. In this case, the ship may need to switch to distillate fuel, lighter, more fluid diesel, for the restart. This takes additional time. Step 3. The start attempt. With air pressure confirmed, fuel flowing, and lubrication oil running, the engineer gives the command to start. Compressed air blasts into the engine cylinders in sequence. The massive crankshaft begins to rotate. The pistons begin to move. Fuel is injected. Combustion begins. If it takes, the engine accelerates to idle speed. The main generators, driven by the engine, begin producing power. The main switchboard comes alive. Full electrical power is restored to the ship. If it does not take, if the engine fails to fire on the first attempt, the compressed air receivers lose pressure with every attempt. There are typically enough reserves for 2 to 4 start attempts before the air supply is critically low. An engineer who uses all available compressed air in failed start attempts and cannot recharge the receivers has effectively used the ship's last resource for propulsion restart. The ship remains dead until the receivers can be recharged, which requires the emergency compressor to run for an extended period, time the ship may not have. This is what maritime engineers call the one-shot problem. In a genuine emergency, close to a coastline or a fixed structure, you may have one realistic attempt at a black start before the situation becomes unrecoverable. The entire sequence, from the first attempt to start the air compressors, through fuel system preparation, to the first firing of the main engine, takes a minimum of 20 to 30 minutes on most large vessels, even with an experienced crew executing the procedure without errors. In the case of the Dali, the distance between the ship and the bridge when power was lost was not sufficient for a successful black start to prevent collision. The crew did everything they could. The physics of the situation, the ship's speed, the distance, the time required, did not allow for a different outcome. The bridge came down. So what actually happens in the first 60 seconds after a ship loses all power? 0 to 5 seconds. The engine stops, the rudder freezes, the bridge goes dark. 5 to 15 seconds. The ship becomes a drifting object, subject entirely to wind and current, with no propulsion and no steering. 15 to 30 seconds. The emergency generator starts. The clock for the black start begins. 30 to 60 seconds. Emergency systems restore critical functions. Lights, navigation, communications, one steering motor. The engineers begin the black start sequence, knowing they have, at most, a few attempts before the air supply is gone. Everything after that depends on how much time the ship has, how much distance it has, and whether the physics of the situation allow the engineering to succeed. In open ocean, time is usually available. The black start succeeds. Power is restored. The ship continues. Close to a bridge, a coastline, or a reef, the margin between a successful restart and a catastrophe is measured in meters and seconds. The engineering is the same in both cases. The outcome is determined by geography. If you want to understand the full power system that, when it is working, prevents this situation from arising, how a ship generates and manages over 100 megawatts of electrical power continuously, I have covered that in the engine room video on this channel. Understanding how the system works makes the failure mode considerably clearer.